How's everybody doing? Tuesday. You know, Monday, Tuesday, Wednesday, and then Friday. Friday really seems like Friday, but Wednesday also seems like Friday, so it'll be kind of a weird thing for us, huh? I tried to get the class changed. This has been taught as Monday, Tuesday, Wednesday, Friday for many years. And this year I tried to get it changed to Monday, Tuesday, Wednesday, Thursday, because it's a logical thing, right? Well, it turns out that there's a lot of conflicts with a lot of schedules, and I was unable to do that. So the powers that be would not let me change it to Monday, Tuesday, Wednesday, Thursday. So it's Monday, Tuesday, Wednesday, Friday against my wishes, but my wishes don't always determine everything, unfortunately. Okay, so I wanted to come back here, show everybody the page. I had some issues with the camera yesterday because when there's nothing on the screen, the camera has nothing to focus on. So for that first part of the lecture where I was talking about all those various things, the camera's going, rrr, 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 trying to focus, and it was very distracting. So I thought that probably wasn't a good idea. So I sort of summarized the things there on the points 1 through, I think, 5 on the schedule page, and then posted the video after the screen came up and the camera was able to focus. So we shouldn't have that problem again. And you'll see that I've also included on here a link to highlights. Highlights are something I write at the end of each lecture that cover what I think were the important points that I talked about during the class. And highlights are what I actually use to write my exams. Okay? So it gives you a pretty good idea about where my mind is relative to exams and so forth that I'm writing. You will see that there will be links in the class that will be on here that I won't necessarily go through. Okay? And the question is, oh, am I responsible for those, et cetera, et cetera. My rule in the class is very simple. If I talk about it in the class, you're responsible for it. And if I don't talk about it in the class, you are not responsible for it. So if there's links I don't go to or there's things I don't go to, that's fine. I'm not going to go back and ask you obscure questions out of the text about something that I haven't talked about. So the rule is if I've talked about it, it's fair game, but only things that I've talked about. Does that make sense? Only things, so you're only responsible for the things I talk about in the class. So your basic line now should be, let's try to keep him from talking as much as possible. Right? You guys are a dead group, I tell you. Okay, so that's those are the highlights there. And let's see. And, of course, the videos are there as well, so the video from yesterday is there. I try to get the videos posted within 24 hours of making them. That doesn't always happen, but I do try to make that happen. I appreciate your patience. Sometimes there are technical problems. Sometimes there's YouTube problems, and it's harder for me to get those up there. But I do try to get them up as quickly as I can so that you can have access to them as you need. Okay, let's go back here and finish talking about what I was starting to talk about yesterday. Okay, so what I hope I left you with yesterday was a sort of a general sort of background relative to cells and relative to macromolecules. Okay, because macromolecules are really what makes cells tick. They're really what makes cells tick. DNA and RNA, of course, necessarily for directing all the functions and all the synthesis of things in the cell. The proteins, as I will describe, are the things that we call the workhorses of the cell because they do most of the things that we associate with cells. And the carbohydrates, of course, are involved in energy storage and energy usage. And so we'll talk a lot about those, especially as we talk about nutrition and other considerations relative to that. And, of course, fat and fatty acids are involved in that as well. Now, what I want to talk about a little bit here before I jump into talking about buffers and water and so forth is energy. So the last thing we have to think about in general with respect to cells has to do with energy. Okay? Cells have to have energy. And we will talk about a couple of reasons why cells have to have energy. It sort of makes sense that they do need to have it. Perhaps the reasons that they ultimately need to have it may not be apparent to you. And they will have to do with osmotic balance, actually. We'll talk about that in a bit. But energy is a very, very important consideration. Everybody knows that's ever taken any biology class that the energy source for cells is essentially ATP, adenosine triphosphate. We talk about ATP being the gasoline of the cells because it's used everywhere in the cell, and it's a very important molecule. I'll tell you something about ATP that still surprises me whenever I think about it. Okay? And this was something I learned myself only a few years ago, but it's a really remarkable thing. Our body makes and breaks the entire body weight of ATP every day. Your body makes and breaks, that is, uses, your entire body weight of ATP every day. Okay? Now that's a lot of ATP. A heck of a lot of ATP if you think about that. Okay? So it tells us that energy generation, energy use is very, very critical for cells. To make ATP, we have to burn things. Okay? Oxidation is the process whereby we derive energy that's stored in the form of ATP. So the way that we make ATP is by burning things. We think of burning fat. We think of burning carbs. All right? Those are the ways that we make ATP. Now, why ATP? Why is ATP the energy source of cells? And it turns out that the reason for that has to do with the fact that ATP has phosphates in it. ATP, the T stands for tri, and the P stands for phosphate. And so adenosine triphosphate is a molecule that has a lot of energy in it. A lot of energy in it. Okay? If we look at ATP, okay, what we see is ATP right here has phosphate, phosphate, phosphate. And when ATP releases its energy, it lets go of one of the phosphates and becomes ADP. So this process that you see on the screen is happening in your body continuously. It's happening in your cells continuously. And this release of energy requires hydrolysis, that is, water coming in and breaking the bond between two of those phosphates. Well, we have plenty of water in our cells, and there are enzymes that help this process to happen, as we shall see. But why is it that ATP has all of this energy? Why does breaking a bond in ATP release energy? The reason that that happens is because ATP itself is a high-energy molecule. We can think of it as storing energy. How does it store energy? Well, it actually has to do with the phosphates themselves. Okay? Phosphates readily ionize in cellular pH, meaning that they lose protons. And when they lose protons, if I lose a proton here, I lose a proton here, and I lose a proton over here, each one of those phosphates has lost a proton. That can readily happen in the cellular environment. Let's think about this. I've got a negative charge next to a negative charge next to a negative charge. What are negative charges going to do? Going to repel each other, right? Do you suppose those phosphates want to stay together? The answer is they don't. So if you provide them with a way to get separated from each other, one of them will, in fact, go flying away. And that releases energy. It's very simple. Okay? Now, you'll see, and I'll complain about the way people teach chemistry and the way that people teach math. And the reason I complain about that is they don't teach students practical things, like I've just told you. You've learned something about the chemistry of ATP without having to go into a whole bunch of mumbo-jumbo to do that. And it was intuitive. It made sense. Phosphate, a negative phosphate repels a negative phosphate, and you try to put two, it's like trying to put two north magnets together, right? They're going to repel. Well, this guy repels in very much the same way, except for here it's repelling with an ion, and that ion being a negatively charged phosphate. Okay, so we understand then how it is that nucleotides like ATP that have three phosphates in them have a lot of energy in them. We'll see later when we talk about other things in the cell that there are other triphosphates that are used for energy in the cell. GTP, for example, is used completely in the synthesis of proteins. All the energy for the synthesis of proteins comes from GTP, not ATP, but the principle is the same thing. The three phosphates are close together. They want to fly apart. You allow them to fly apart. They release energy. Okay. Now, this energy that cells have can do some really remarkable things. Okay? I like to use this example of the electric ray. Okay? The electric ray is basically electricity that's generated by organs of this electric ray that the organism uses to stun and kill its prey. Okay? It's one of the more bizarre uses of energy in any living system that's on the face of the earth, but it's a pretty cool system. And it tells us that cells can use chemical energy to do incredible things. We use chemical energy to contract muscles. We use chemical energy to see with our eyes. Something like about a quarter of all the energy in our body is used by our eyes. Okay? When people starve themselves to death, one of the things that happens before they actually do starve to death is they go blind. They go blind because the eyes requiring that energy don't have the energy that they need to give vision. Our brain uses energy. Our cells use energy to talk to each other. Okay? Our cells use energy to make proteins. Okay? So cellular energy can be used for a variety of things, and the electric ray is one sort of odd example of that. All right, questions about that? This is a quiet group. You guys won't ask any questions. I'll have to do something silly in order for you to ask a question. All right. All right. Let's turn our attention now to something that's going to scare some of you. All right? Now that I've given you that warning, I'll get your attention, right? I'm going to scare some of you because you're going to look at this and go, oh my God, this course is going to be all about calculations and numbers and blah, 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 blah. Okay? And it scares people because the first thing I talk about are things that relate to numbers and calculations. I try to keep the numbers and the calculations simple, okay? But it's the first thing you're going to see in the course. If you're anxious about math or you're anxious about what these things mean, all right, this is a time that you'll get anxious. I will assure you this is only the first part of the course. But we have to talk about it first because in order for you to understand some of the principles we'll talk about later with respect to charge, repulsion, attraction, things I talked about yesterday, in order to understand those, we have to understand what happens in water. Okay? Now I'm going to go back to your freshman chemistry. I'm going to go back to something that you all thought, I'll never have to think about this again. I see a lot of smiles with that. Okay? Everybody's going, oh, yeah, we love thinking about freshman chemistry. How many people loved freshman chemistry? A few did? Okay, good. I don't usually see that many hands, so maybe this is a good sign. I won't ask how many didn't because I know, truth be told, that a lot of people didn't like freshman chemistry. I'm going to tell you some things in a different way than you were told in freshman chemistry because, like I said, I like to teach chemistry and I like to teach math from a practical perspective, and that's largely what I'm going to do today and I'm going to do tomorrow. Okay? Practical means things that you can use, things that you can understand. And one of the reasons I told you yesterday I don't let students in my other class use a calculator is because they turn their minds off when they put a calculator in front of them. They turn their minds off when they put a calculator in front of them because numbers simply become that with a calculator. And as I hope to convince you, there's a lot more to numbers than the numerical value. Okay? All right. Well, before I talk about numbers and before I talk about calculations, I need to introduce the topic of water. Okay? Now, one of the things you learn in freshman chemistry is electronegativity. If I said to you, what's the definition of electronegativity, how many would feel, I'm not going to ask you to give me the definition, but how many would feel you could give me a good definition of electronegativity? One, oh, a few. Okay, okay. If they're all on this side of the room, I'm not sure why that's the case. So, but you guys over here not get electronegativity, or what happened there? Or you just happen to sleep over here, maybe? Okay. Electronegativity is a measure of the attraction that a nucleus has for electrons. That's what it is. It's a measure of the attraction that a nucleus has for electrons. Something that has a high electronegativity, like oxygen, has a very great attraction for electrons, meaning it pulls electrons close to itself. I'll repeat that. Something that has a high electronegativity pulls electrons close to itself. Something that has a less high electronegativity doesn't have that pull, right? Okay. Water, of course, is made of H2O. We see that water has one atom that has a high electronegativity, and it has two atoms that have a lower electronegativity. The hydrogen's electronegativities are not additive. Water looks like this. Water, you may have learned in freshman chemistry, is a bent molecule. No, we don't care about the angles, blah, 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 right? It's a bent molecule. And if we look at this molecule, in the middle we have oxygen, and on either side we have hydrogen. I told you that oxygen has a greater electronegativity. Oxygen, therefore, grabs electrons and holds them closer to itself. Oxygen and hydrogen are in a covalent bond, meaning they share electrons. That's a good thing to know. Covalent bonds involve sharing of electrons. Ionic bonds involve gain and loss of electrons. Sodium chloride has ionic bonds because sodium gives up its electron to chlorine, which takes it. Okay? But water has covalent bonds. How do we know the difference between the two? Well, if you want to memorize something, you can. I'll just tell you, but you don't need to memorize this, and that is that they have reasonably close electronegativities. Okay? Reasonably close. Oxygen and hydrogen's electronegativities are not that far apart. But they are farther apart. Oxygen has a greater tendency to pull electrons than hydrogen does, so oxygen in this molecule is the bully. Oxygen grabs the shared electrons and holds the shared electrons closer to it. Well, hydrogen only has one electron. When it gets in this tug of war with oxygen, it loses the tug of war. Oxygen holds the electrons closer. Hydrogen is seeing its electrons further over there. This results in what we call a partial charge. A partial charge. If hydrogen completely gave up its electrons, it'd be a full charge. But it's not completely giving up its electrons. Okay? Hydrogen is therefore partially positive. That's what that delta there is. Okay? It's partially positive, and oxygen is partially negative. And this very simple fact gives rise to life on Earth. It gives rise to everything that we know on Earth. Okay? This very simple fact that you see on the screen, if you want to know one secret about life, it's actually contained right there on the screen. We're going to talk over and over about how this property of water gives rise to so many things. This is pretty magical. Okay? It's a very simple thing. Hydrogen is partially positive, oxygen is partially negative. You learn in freshman chemistry this gives rise to something we call hydrogen bonds. Okay? Hydrogen bonds arise from partial charges involving hydrogen. I'll repeat that. Hydrogen bonds arise from partial charges involving hydrogen. Okay? We're going to see hydrogen bonds appearing over and over and over. You may get sick of hearing about hydrogen bonds because they appear all the time. Is that a question? Oh, you're just waving at me there. Okay, that's fine. Okay. Makes sense? All right, so that's what a hydrogen bond is. We could imagine that if I have a zillion of these water molecules, a water molecule over here that has two hydrogens and an oxygen is going to orient itself relative to this one in such a way that the positive is going to be attracted to the minus. And we can imagine this will go on and on and on and on and on and on and on throughout the solution that's water. And it turns out that that is, in fact, the case. Okay? that there's an orientation that happens as a result of these partial charges. Okay? I'll come back to that. All right? Here's what I'm talking about. Here, for example, is water. You can see water has partial positive charges. It has partial negative charges. If I have just water, then I will have those interactions that I just described to you. The hydrogens interacting with the oxygens interacting with the hydrogens. Okay? These occur in 3 dimensions. It's not just flat like we draw it on the screen. But water has another property. Water dissolves things. Water doesn't dissolve everything. You know water doesn't dissolve oil. What's that? Well, detergents affect that, certainly. Right. Okay? But water dissolves things because of hydrogen bonds. Let's imagine I take sodium chloride, or in this case potassium chloride, and I add it to water. Well, I told you that sodium chloride or potassium chloride makes ionic bonds, meaning that chloride gets the extra electron from either the sodium or the potassium, which means that chloride ends up being negatively charged, and the sodium or the potassium becomes positively charged, giving up its electron. All right? What do you suppose water is going to do when it sees something that's positively or negatively charged? Well, those hydrogen bonds are going to come into place here, and you can see it happening on the screen. Here's the partial positives of the hydrogen. They're attracted to the negative of the chloride. They'll make a nice little wall around that chloride in 3 dimensions. Here's the oxygens making a little wall around the potassium. Okay? Things that are hydrophilic, you hear that term, hydrophilic. Hydrophilic literally means likes water. It means that they have something about them that is polar or charged. Things that are hydrophilic will have something about them that is either polar or charged. Here we see charged. We could just as easily see it polar. Look above. Above we see an alcohol. And an alcohol, you should recall, is something that has an R group. It has an oxygen and it has a hydrogen. Oxygen is going to be partially negatively charged. Hydrogen is going to be partially positively charged. And now that interaction with water is going to be very much like we've seen before. The hydrogens interacting with the negatively charged water, the oxygen interacting with the positively charged hydrogen over here. Okay? Alcohol is not ionic. It's not charged. It's only partially charged. And because of this partial charge, okay, water will dissolve alcohol. We mix alcohol with water, we get a good mixture, okay? Those of you who are brewers know this very well, okay? You don't see the alcohol in wine or beer separate out. It mixes with the water, and it's mixing because of this that you see right here. Okay. All right. Oil and water, however, don't do that. If I take oil and I mix it with water, I get 2 layers. I get a layer of oil and I get a layer of water. And when you see 2 layers, it tells you that oil doesn't have polar or ionic mixture in it. Okay? Oil is nonpolar. So nonpolar substances will be what we call hydrophobic. They will not dissolve in water because they don't have polar components, and those polar components arise from either ionization or hydrogen bonds. They don't have it. They don't have that, or at least they don't have sufficient amounts of that. Hydrophilic, we see sodium chloride, we see polar compounds, we see weak acids. Weak acids, as we shall see, ionize to some extent. And we see sugars. Sugars and carbohydrates will interact with water because we're going to see sugars are full of hydroxide groups. And hydroxide groups have oxygen and hydrogen, and we're going to give rise to the same kinds of interactions we've already seen with alcohols. Okay. Hydrophobic compounds are not going to interact with water. They're not going to dissolve in water, and that's because they don't have any part of them that's polar. They can't make hydrogen bonds. They can't ionize. Therefore, they will not mix with water. Now, lipids like fats and cholesterol, from a nutritional perspective or from a medicinal perspective, turn out to be really interesting when we study them in the body because they've got to move in the body, but they don't dissolve in water. Sugar dissolves in water. Our body uses sugar as a very rapid energy source because our liver can dump sugar into our bloodstream and it travels, bingo, to the muscles and in seconds make an enormous difference. That doesn't happen with fats. We don't use fats as a rapid source of energy because fats have to be properly prepared and packaged so that they can travel in our bloodstream. If we dump fat into our bloodstream and we didn't package it, we would get globules that separated out. We would probably have a stroke. Not a good thing. Okay, hydrophobic versus hydrophilic. Amphipathic. What's amphipathic? Okay. Amphipathic describes a property of a molecule that has both properties. Part of it will, in fact, ionize, or part of it will be very polar, and part of it will be very nonpolar. Okay? It's the bipolar, to use a psychological term, it's the bipolar molecule in our cells and in our bodies. Okay? Some really good examples of bipolar molecules are fatty acids. And fatty acids are used to make detergents, as he's talking about over here. Detergents are really good because part of them will interact with water and part of them will interact with nonpolar things. We wash our hands with soap because the polar part of the fatty acids in soap are soluble in water, and the nonpolar part grabs a hold of the nonpolar substances like grease and makes it soluble. Okay? All right. We'll talk more about fatty acids as we get going further along. All right. Well, there's a good example of water all by itself that I talked about earlier. You start to envision it now in 3 dimensions. No, I'm not going to ask you to draw it in 3 dimensions. Okay, I don't expect too much artistic ability because I don't have any artistic ability. Okay, but you can see negative with positive, positive with negative, etc. We can have more than one positive attracted to the same negative, etc. Okay. Question? No question? Okay. All right. Well, hydrogen bonds can happen in a variety of things. We talk about it with respect to water, but many of the compounds that are in our cells form hydrogen bonds very readily. The first thing we'll talk about that makes really good hydrogen bonds are proteins. Proteins have oxygens in them, they have hydroxide, they have hydrogens in them, and we'll see they also have amines. Nitrogen has a very similar electronegativity to oxygen. So nitrogen is capable of pulling those electrons away from hydrogen, just like oxygen is, and give rise to a hydrogen bond, just like we saw before. So in this case, this nitrogen would be partially negative, this hydrogen would be partially positive, and that would be attracted to the partially negative oxygen that's here. Well, nitrogens are all over. Amino acids, amino means nitrogen. Amino acids, which make up proteins, are full of nitrogen. So we can imagine that there's a lot of hydrogen bonds that happen inside of proteins. Okay? There's some more examples. An amino acid with an amine, hydrogen bonding with an oxygen, okay? And other things, hydrogen bonding as well. Now, well, wherever we have an attraction or we have a repulsion, we have an energy associated with that. It takes energy to break bonds. It takes energy to break hydrogen bonds. Okay? Well, if we look at the strength of bonds, how much energy, this table is showing you how much energy it takes to break these various bonds, we see, first of all, that covalent bonds are the hardest bonds to break. Okay? The hardest bonds to break, on the order of about 450 kilojoules per mole. You don't need to know that number. Don't worry about that number. Okay? But that's a lot bigger than hydrogen bonds. Hydrogen bonds are only about 20 kilojoules per mole, meaning that a covalent bond is about 20 times as strong as a hydrogen bond. Now, that doesn't mean that hydrogen bonds aren't important or that they don't influence things, because they have enormous influence on things. Okay? They have enormous influence on things. This shows the boiling point and the melting point, okay, of three compounds that have very similar molecular weights. Water, which has a molecular weight of 18, ammonia, which has a molecular weight of 17, and methane, which has a molecular weight of 16. If their boiling points were a function of their size, they should all have very similar boiling points. But look at the temperature that water boils at. It's 100 degrees centigrade or 212 degrees Fahrenheit. Ammonia boils at minus 33 degrees centigrade, and methane boils at minus 161. Why does it take so much more energy, meaning greater temperature? Why does it take so much more energy to boil water than it takes to boil these other two compounds? These other two compounds don't form hydrogen bonds to the extent that water does. So now we see that those hydrogen bonds, in summary, do have a very important effect, and the effect is seen here. It's also seen in the melting point. It's reflected exactly the same way. So water is literally holding itself together with hydrogen bonds. One water molecule is attracted to another water molecule, which is attracted to another, and they hold each other together as a result of that. Hydrogen bonds have a very big effect on melting points and boiling points. Okay, well, I've introduced the topic of hydrogen bonds. I want to move away from hydrogen bonds, and I want to talk about ionization. Ionization involves the loss or the gain of protons. All right? I'm going to repeat that. Ionization, from our perspective, from a biochemical perspective, involves the loss or the gain of protons. Here is some ionization. Okay? I draw a very simple scheme for ionization. I'm going to introduce this to you, and it's going to be a little different than you saw in freshman chemistry, but I hope mine is simpler than what you learned in freshman chemistry. How many of you love learning what a conjugate acid and a conjugate base and all that blah blah was in freshman chemistry? You like that? Yeah, you're a nerd. You win. I hated that. What did that mean, right? I like to use two terms, acid and salt. Everything we're going to describe in this class about ionization can be described as an acid and a salt. Everything. Okay? We're not going to use the term base, except for one purpose. We will use the term base when I describe a strong base. What does a weak base mean? I have to scratch my head and think about what that means. What does a weak base mean? I'd have a hard time giving you a definition for that. Okay? A weak acid, but a weak base? I don't know. Weak base is hard to think of, hard to conceptualize. All right, I've got an acid and I've got a salt. This is the schematic I use for any kind of an acid. This is the schematic I use for any kind of a salt. What's the difference between an acid and a salt? It's very, very simple. The difference between an acid and a salt is that an acid will always have one more proton than a salt. One more proton. You can see the proton has been lost here. If this were hydrochloric acid, we would have HCl on the left, we would have H+, and we would have Cl- on the right. Okay? Everybody follow? Well, HCl turns out to be a pretty bad example, because HCl is an example of what I call a strong acid. We don't have strong acids we're going to talk about in biochemistry. We'll use strong acids to change things, but biochemical acids are not strong. They're not strong acids. They're weak acids. Well, what's the difference between a strong acid and a weak acid? Okay, here's a definition. If you want to write a definition down, maybe a good one. Okay, A strong acid completely ionizes in water. A strong acid completely ionizes in water. A weak acid, therefore, does not completely ionize. Now, what does that mean? I'm going to give you an example in just a second. Okay? Let's imagine I had a weak acid. Well, let's imagine I had a strong acid to start. Let's say I had HCl. I have HCl. I put it into water. I start with 1 million of these, HA, and I put it into water. What's going to happen is I will get 1 million protons, and I will get 1 million chlorides, and I will have 0 HCl left. And that's what you learn in freshman chemistry. HCl, it's a strong acid. It completely dissociates. If I know how many of these I started with, I know how many of these each I end up with. It's the same number. Okay? A weak acid has a very different property. A good example of a weak acid, one you'll hear me give a lot of examples of in class, is acetic acid. Okay? Acetic acid has a hydrogen linked to an acetate. That's why it's called acetic acid. I will frequently write it as HAC. The AC to indicate the acetate part, and the H to indicate the proton that can come off. If I started with 1 million, and here's the place where about a third of you are going to immediately lose me, or I'm going to immediately lose you. So if you pay attention here, you may learn something very important for the exam. If I start with 1 million acetic acids, HAC, and I put it into water, I will not get 1 million protons, and I will not get 1 million acetates. It's a weak acid. It does not completely come apart. In fact, if I put this into water, what I will get is a few thousand protons and a few thousand acetates, and I'll be left with 990,000 some undissociated, unionized acetic acids. That's different than what we saw before. Okay? Everybody understand that difference? Very, very important thing. All right? So a weak acid, when I put it in water, I'm going to have some of it over here. I'm going to have some of it over here. All right. If I start with the hydrochloric acid, and I know how many of these I end up with, I can pretty quickly calculate the pH from a very simple equation. You learned an equation in freshman chemistry that said pH is equal to the negative log of the hydrogen ion concentration. Okay? You punched it into a calculator and you got that number. So if you decided that you had 0.1 molar H+, you plugged in 0.1, you took the negative log of 0.1, okay, and you saw that it had a pH of 1. That's what you would see. Okay? That's because I know how many of these guys I start with. I don't know in the case of acetic acid. Weak acids have different rules, and we have to use those different rules to calculate their pH. And what we're going to see of weak acids is we can change how much salt we have and how much acid we have by changing the pH of the solution it's in. I can add a strong acid to that solution. I can add a strong base to that solution, and both of those are going to change the pH of that solution. And when they change the pH of that solution, the balance of these is going to change. I'll give you an example. Okay? How many people could tell me Le Chatelier's principle? 1, okay. Maybe 2, okay. Le Chatelier's principle says that you put a system under stress, and the system will respond to that stress. If I put you under stress, you're going to respond to that stress, and hopefully you'll respond in a positive way. Exams are known as stressors, right? Okay? Here's my system. Let's imagine I have this system. I've taken my acetic acid, I've poured it into water. I get some of the protons, I get some of the acetates, and I got a lot of things left over here. Let's imagine I take that solution and I add a strong base to it. I said I was going to use the term base in one case, and its one case is right here, the strong base being sodium hydroxide. What is a strong base? Well, a strong base completely dissociates in water, just like a strong acid completely dissociates in water. If I take a strong base like sodium hydroxide and I add it to water, it will completely come apart. I will have sodiums and I will have hydroxides. What do hydroxides do? This is the part about freshman chemistry that disturbs me that people don't get taught. Hydroxides love protons. They will react with protons, and when hydroxides react with protons, they make water. What's that? Water, yes. Is that? Okay, yes. Did I not say water? Oh, okay. Sometimes I say the wrong thing, so I have no problem with being corrected. All right, they make water. All right? Now, let's imagine I've got this solution. I've just dumped a bunch of hydroxide into there from sodium hydroxide. What did I just do to this system? I just disturbed the system, didn't I? Didn't I just pull a bunch of protons away from this equation? Le Chatelier's principle tells me the system is going to respond to that pulling away of protons. How do you suppose the system is going to respond? By making more protons. And how's it going to make more protons? Well, remember, we had a whole bunch of undissociated HAC over here. Some of these guys are going to say, oh, we'll replace what got lost. Let's imagine, if you will, that I dumped in, I don't know, let's say 1,000 hydroxides into that solution. When I dump 1,000 hydroxides in that solution, I'm going to lose 1,000 of these to make up 1,000 protons to replace that which got lost. My net amount after that will be my starting amount less the number of hydroxides I put in. But now this is going to gain, the salt is going to gain by 1,000 also. Because whenever I break one of these down, I get one of these, and I get one of these. Are you guys with me? Everybody's with me? Be honest. This is important, okay? Yeah? Sure. Le Chatelier's principle. Well, I reiterate that. So Le Chatelier's principle says that if I take a system that's at equilibrium and I disturb it, it will respond to that disturbance. And it will respond to that disturbance to alleviate the stress. That's really technically what it says. So in this case, I've taken away protons. The system responds to alleviate that loss of protons by replacing those protons. Okay, everybody with me? Well, what's just happened? I've changed the amount of salt. I've changed the amount of acid. And it turns out that the pH of that solution is a function of the salt and of the acid. Okay. Now I'm going to come back to this equation that you see on the screen. I'm not going to explain it to you for the moment. But I just want you to understand the principle of what I've talked about. Everybody understand the principle? I've disturbed the system. When I disturb the system responds to try to alleviate that disturbance. That was Le Chatelier's principle in action. Okay? Okay. Okay. Now, here's the equation that you saw on the bottom right of that screen. It's called the Henderson Hasselbalch equation. And the Henderson Hasselbalch equation needn't cause panic, but it does. Okay? When we talk about weak acid systems, we cannot use pH equals negative log of the hydrogen ion concentration. We have to use Henderson Hasselbalch's equation to determine the pH. That means we need to know how much salt is in there and how much acid is in there. And we use this equation, which has another term in it called the pKa. What in the hell is the pKa? The pKa is a measure of the strength of a weak acid. The strength of a weak acid. I've already told you it's not strong, but now you begin to get the idea that there's a variety of strengths of weak acids. Let's take a look at some of these. Okay? Here are some weak acids. Oh, wrong one, sorry. It's this one. Here are some weak acids, okay? There's acetic acid I've been talking about. There's what it looks like. There's the acid form, and there's the salt form. And I can tell the difference because the acid form has one more proton than the salt does. And I can look up in this table, and I can see that acetic acid has a pKa of 4.76. By the way, on the first exam, I will give you every equation you need to know. You will not have to memorize pKa values or anything like that. I will expect that you will know how to use equations, not memorize equations. Does that make sense? Learning to use equations makes more sense than memorizing equations. So I'll give you every equation you need to know. Okay? The pKa of acetic acid is 4.76. The pKa of any acid is a constant. Only weak acids have pKa values. Whenever you see a pKa value, the first thing that should pop into your mind is weak acid. Okay? The lower the pKa of a weak acid, the stronger the weak acid. If we compare acetic acid, which is a 4.76, to formic acid with a 3.75, we can say that formic acid is a stronger weak acid than acetic acid is. They're both weak, but formic is not as weak as acetic acid is because its pKa value is lower, and things that have a high pKa value, like carbonic acid here, things that have a high pKa value are therefore weaker weak acids. Okay? Now you'll see some of these guys have more than one pKa. Carbonic acid was a really good example. It's got two different pKa values because it's got two different protons that can come off. Okay? Each one has a characteristic value, and no, you don't need to worry about which one is which, but the point is the first one comes off with a pKa at 6.37, and the other one comes off at a pKa of 10.2. Okay? pKa's are constants for a given weak acid. They will always be the same. Always. All right? Now, that becomes a very important consideration. Let's go back to our Henderson Hasselbach equation. All right? Henderson Hasselbach equation is right here. pH equals pKa plus the log of the concentration of salt divided by the concentration of acid. Let's go through a couple practical examples. And I may run over a couple minutes here because I want to get through this point before I finish today. Okay? If I wanted to know the pH of a solution of acetic acid, and I told you that acetic acid had a pKa of 4.76, which I just told you, and I told you that you had equal amounts of salt and acid, could you tell me what the pH value was? Well, you'd say, if I had a calculator, and that's because you learned to do logarithms on a calculator. Now, I'm not going to ask you to do logarithms, the numbers of logarithms, but I'm going to ask you to learn the values of logarithms. This is the practical math. There's 3 rules about logarithms that you should know. Number 1, the log of the number 1 is 0. The log of a number greater than 1 is positive. And the log of a number that's less than 1 is negative. That's pretty simple. The log of 1 is 0. The log of a number greater than 1 is positive, and the log of a number less than 1 is negative. So I just told you I had a solution of acetic acid that had equal amounts of salt and acid. And I said, what's the pH? Could you tell me what the pH is? I would hope you would be able to tell me the log term is 0. Therefore, the pH of this solution was 4.76. You didn't use a calculator. Let's imagine that I had a solution of acetic acid, and I had more salt than I had acid. Is the pH greater than 4.76, or is the pH less than 4.76? It's greater, because if there's more salt than acid, this ratio is greater than 1, and the log of a number greater than 1 is positive, and a positive number plus 4.76 is going to give something that's greater than 4.76, right? No calculator, guys. You didn't use a calculator for that. If I told you that the pH of a solution of acetic acid was 4.0, tell me, is there more salt in there or is there more acid in there? More acid, but we'll get this very quickly. Because that means that this term has to be negative. And in order for this term to be negative, that ratio has to be less than 1, which means there must be more acid than there is salt. You didn't need a calculator, guys. This is empowering. You can learn something about this by learning about numbers instead of futzing with numbers. We're not going to futz with numbers. We're not going to futz with numbers, okay? That's important. All right. I always like to, as I've said before, finish a lesson with a song. Let's finish with a song. It's entitled Henderson Hasselbach, okay? Henderson Hasselbach, you put my brain in shock. Oh, woe is me. The pKa's can make me lie in bed awake. They really give me bad headaches. Oh, hear my plea. Salt acid ratios help keep the pH froze by buffering. They show tenacity, complete audacity, if used with incapacity to maintain things. I know when H's fly, a buffer will defy them actively. Those protons cannot waltz when they get bound to salts. With this the change in pH halts. Oh, praise to thee. Now that I've addressed this topic for the test, I've got know-how. The pH I can say equals the pKa in sum with log of S or A. I know it now. See you guys tomorrow.